Hello and welcome to this lesson about problem-solving distance problems. The learning target for this video is setting up and solving one-direction distance problems. So let's talk about the basics with distance problems. First of all, distance problems all rely on some variation of this formula right here. D is equal to rate times time. And we're usually going to be talking about two people. So we'll have these little submarks down here to denote one person, and then we'll have another one for a second person. So D2 is equal to R2 times T2. And the real trick is to say all of this without accidentally making a Star Wars reference. So we are using this formula. The next thing is that we have essentially two main types of problems. There are others out there, but there are two big types that these problems tend to fall into. Type 1 is same direction. And so when we're talking about same direction, it's a situation where you have two people and they're going somewhere, but usually the second person waits a little bit and then they end up going much faster than that second person, but they have to somehow catch up to that, or sorry, I mean the first person, they have to catch up to the first person. All right, and so when we're talking about same direction, what we're really curious about is when this distance is equal to that distance. And so our method for solving same direction is D1 equals D2. Now, when we're looking at, or the second type of problem we have is different direction. Different direction. Different direction problems can go one of two ways. You have people who are either starting off at the same location and then they are going in different directions, or they're at opposite ends and they are meeting up in the middle or something like that. Now, what usually is going to happen is we're going to ask, how far are they after 2 hours, after 10 minutes, after 5 seconds, whatever it is, or how long will it take them to meet up. So what we're looking at here is the sum of their two distances. And so what we're looking at is D1 and D2, D1 and D2, and what does that look like when they're together and added up? So if we're dealing with different direction, we're going to use D1 plus D2 equals total distance. Now, we're not going to worry about that one today. That's a problem for another time. We're going to focus on same direction, where they're going one direction. So we're going to use D1 equals D2. Now, we're not quite done with how to describe all these. So let's talk about a few more sort of loose ends about the basics before we do some examples. So one thing that's super critical that we have to do is make sure our units match up. All right? And so what could happen is we're going to talk about people who are going 10 miles per hour, but we may say 20 minutes later. We have to make sure that the units match up. All right? And so I'll go through that with some examples. So especially with time and speed. Time and speed. All right. The other thing that we have to understand is that there is a... let me change that up. A lot of ways to do these correctly, but not get the right, in quotes, answer. So there are many ways you can set up these problems, but it boils down to answering the question asked. Answer the question that was asked. That was asked. Oops. And I'll show you again what that kind of looks like in a minute here. So you just have to keep that in mind. And the final loose end that I want to talk about is that our answers might not be pretty. So fair warning, we're going to have some awkward decimals. So just we're going to have to deal with it. Might not be pretty. But this is why we tend to use calculators for these problems. So let's look at our first example. Max goes on a bike ride, riding his bike at 12 miles per hour. An hour later, Steve rides his bike going 20 miles an hour. How long until Steve catches up to Max? Okay, so let's just kind of loosely draw this out. We got Max, we got Steve. Max goes 12 miles per hour. Now, Steve, he's just going to sit here for a whole hour and do nothing. But then eventually, he's going to ride his bike, and he's going super duper fast. He's going 20 miles per hour. When do they catch up? So that's the question mark right there. And so what we have is a D1 equals D2 situation. And what I'm going to recommend we do is that we use another magic box. So our magic box for this one is going to be D1, D2, and then we'll have R and T. And the point of this is to help us organize our information. So let's look at the problem. D1, let's just call him Max, is going 12 miles per hour, and the time is unknown. All right? Now here we have to use some reading, and we have to think. And this is why we can set up the problem many different ways, get the correct mathematical answer, but maybe not have the right answer. An hour later, Steve goes 20 miles per hour. But now what we're going to need here for his time is an expression. How long has Steve been riding his bike compared to Max? Well, here we can use some numbers. If Max had ridden his bike for 2 hours, Steve has ridden his for 1. If Max has ridden his bike for 5 hours, Steve has ridden his for 4. And what I'm doing here is I'm just taking whatever that time is that Max had, and I'm subtracting 1 from it. So my time here is t minus 1. Now I've set up the equation, and I can bring it all together. Or I have the pieces to set up the equation and bring it all together. So I'll get 12t is equal to 20 times t minus 1. From here, I solve. So I distribute 12t is equal to 20t. Be careful with the distribution here. Minus 20. I'll subtract 20t from both sides. So I'm looking at negative 8t is equal to negative 20. You divide by 8, and we get t to equal 2.5. Now, we got to think, what is this 2.5? It's 2.5 hours, but for who? Who was riding for 2 hours? T. And remember, this represented Max. So Max rode for 2.5 hours. So when it comes to the answer, we have to look at the question. And this one's kind of vague. How long until Steve catches up to Max? Well, 2.5 hours after Max started riding his bike. Meaning, it only took Steve 1.5 hours. So Steve, 1.5, whereas Max was 2.5. And the reason why, so this one has multiple right answers. It's a very vague question, but it all depends on, where did we set t? What does t represent? And t represents Max's time. All right, now let's look at another example. It's a similar example. We still have Max, we have Steve, we have 12 miles an hour, we have 20 miles an hour, but now we're changing it up just a little bit. So what I'm going to do is make my magic box, R and T, and then I got D1 and D2. So Max is riding his bike, he's still going 12 miles an hour. Steve rides his bike going 20 miles per hour. How long will Steve have to ride his bike until he catches up to Max? But he leaves 30 minutes later. Now, look at the question. How long will Steve have to ride his bike? Let's let Steve's time be t. And then what we're going to do is we're going to write an expression of t with Max's. So if Steve started 30 minutes later, that means that Max is going for 30 minutes more. Now here's the issue. 30 doesn't match up with miles per hour. We're talking about 12 miles per hour, and he's gone 30 minutes. So 30 minutes needs to be translated to hours. And so 30 minutes is actually 1/2 of an hour. So instead of saying 30, we need to say 1/2. And so that's what I meant earlier when I said we have to have some similar units for time and speed. We can't have minutes and then miles per hour. We have to have them be the same. Now we're playing the same game. We have 12 times t plus 1/2, or t plus 1/2, equals 20t. We'll get 12t plus 6 is equal to 20t. Subtract 12t from both sides. 6 equals 8t. Divide t by 8 and both sides by 8. We get 6/8, which is equal to 3/4. And 3/4 of an hour is 45 minutes. And so, again, here we have a couple options for the answers. It could be 3/4 of an hour. It could be 45 minutes. And we're choosing to do that because the question asks for how long will Steve have to ride. If I flipped it around and I asked, how long would Max be riding until Steve caught up to him, we would then have to add in that extra half hour to get 75 minutes, or an hour and 15 minutes. So again, depending on how you set things up, you can do everything perfectly well mathematically, but you may not answer the actual question. So just be careful of that. All right, now let's look at one final example. Max goes on a bike ride, riding his bike 12 miles an hour. 30 minutes later, Steve starts riding his bike and catches up to Max 50 minutes later. How fast was Steve riding his bike? Well, the point of this problem is to show you that we might not always solve for t. And again, this is where the graphic organizer comes in handy. D1, D2, R, and T. Well, for Max and Steve, Max is going 12. Steve is unknown, so we'll say X. Now, here's again where we have to think. 30 minutes later, Steve rides and catches up to Max in 50 minutes. So that means we have to go 30 plus 50, which is, let's see, 80 minutes. So he's gone for 80 minutes, but we again need to convert that. So let's see here. That's how long Max has been riding. So he's been going for 80 minutes. And Steve was riding for 50 minutes. But we now need to convert those to hours. And so the easiest way to do that is just to take your time and put it over 60. And since we're going to be playing with these numbers anyways and using them, we don't necessarily have to simplify them all the way. So I might just say 8/6. And then here, if I do 50/60, that gives me 5/6. And so I can use that fraction and just let it kind of be. So here, 5/6. All right. And also, maybe it's nice to have a common denominator. Might make our life a little easier. All right. So anywho, we now do the thing where we're going to multiply these together and set them equal to each other. So we'll have 12 times 8/6 is equal to 5/6x. We can simplify. So 12 and 6, that becomes 2 and 1. So we're looking at 16 is equal to 5/6x. In order to simplify or solve with the fraction, I multiply by the reciprocal, 6/5. So that all goes away, and I get x. And unfortunately, this doesn't simplify that well. I get 96/5. And then from there, I can use a calculator, or I can crunch some numbers to find out that x equals 19.2. And then I just have to think about, what does this represent? Well, I go back up here. Oops, got my eraser on. Go back up here. X was a time. And so if x equals 19.2, that means that is miles per hour. Okay, so I get it. This is a lot to process, but it boils down to setting up the table. So let's start with that. We'll work on interpreting the problems, and we're going to obviously spend a couple days on this. But if you have any questions in the meantime, please let me know.